Hello and good morning from the studio. It might also be a good afternoon for you. So welcome to today's webinar. We will hear about motor protection. So it's session number 2 in our tutorial series around motor protection. I'm Michaela Mönikes. I'm happy to guide you through this webinar today. You might have met me on one of the exhibitions on the Siemens booth. And we will have a vivid session. I mean, if you already joined session number 1, you might already know we invite you to place your questions in the upper right field in the question to the speaker. And at the end of each short presentation block, we will take at least some questions to the expert, and he shall be able to deliver answers. So while mentioning the experts, I'm really happy to welcome my dear colleague Klaus Wagner once again here in the studio, because
Hello.
Klaus is definitely our motor protection expert. He will share his knowledge with you. So he's the expert. Ask your question. And I think now let's directly jump in. You'll probably have, again, some things to share with us.
Yeah.
So Klaus, the stage is yours.
I hope so. Yeah, also warm welcome from my side to all. Short introduction, my name is Klaus Wagner. I'm the product lifecycle manager for motor protection, for C-Protect 5 motor protection. And today in this second tutorial, when you missed the first part, make sure that you also get that part. In the second tutorial, I will talk about the thermal overload protection of the rotor. This is one big topic. You will see we will have several functions to do that. Then we have an additional function called load jam protection. I will also talk about that. In the second part, I will go through a complete setting example. So I have some motor data sheets with motor data, and we discuss the settings step by step for all the functions. And finally, I would like to present you some additional functions which are around C-Protect 5, and one special thing which is an additional function for motor protection. Okay, let's go directly into the topics. A short refresher. We had this slide already in the first tutorial, just to make a short summary and to come all together to the same level. Thermal overload protection of a motor. So on the one hand, we have an overheating of the stator during continuous operation. This is normally during continuous operation. Therefore, we have the thermal overload protection stator function. Then for the rotor, thermal overheating of the rotor, there we have on the one hand the starting time supervision, and this is if the start is too long or if we have a locked rotor situation. And we have a second function which is against too frequent starts in a row. This is what we call restart inhibit protection. You see also the ANSI numbers here in front of these functions. Then a third effect is negative sequence current on the rotating rotor, on the motor which is running. This can be caused on the one hand by loss of one phase, complete loss of one phase. Then we get a very big negative sequence current. And here we have to react relatively fast. So therefore, we have a negative sequence current protection. On the other hand, I can get negative sequence currents due to unsymmetrical voltages on the motor, and this causes me only small negative sequence currents. They have a thermal effect, overheating of the rotor as a consequence, and therefore we have the so-called unbalanced load protection. The difference between both, again, is the one is just an independent, like an overcurrent protection. The other one has a thermal model behind, so it calculates the temperature consequences out of this negative sequence current. Then we can have an overheating of the bearings. So here we cannot do anything by measuring currents or voltages. Here we need sensors at the bearings, and we can also integrate them into our C-Protect 5 devices. And at the end, we can also get overheating of the plant as such. If, for example, the drive is unloaded, the machine is unloaded, this is not a problem for the motor. This is a problem for the working machine. but we can support this as well by watching on the current. So here we have an undercurrent or an underpower protection function as an option to protect these working machines, the loads. Okay, let's go directly into the, maybe a little bit difficult topic. I will give this just as a rough overview. How do we make the overload protection for the rotor? It's calculated independently from the stator overload protection. So we have two separate functions. However, what we use here for the rotor is based on the same thermal single body model, according to, you see the IC number there, as we use it for the stator overload protection function. Here is this equivalent model. I will not go too much into detail. It's called single body model because we have one thermal capacitance here and a thermal resistance. And I bring in here a power loading up this capacitor, and this delta V, the voltage difference, which we would get in an electrical equivalent model, is now here a temperature difference here, which comes from the power which I put in here. And then power is going off via into the ambient, so via one thermal resistance. So we get here a differential equation, which we can solve. And if you want to know a little bit more about that, make sure that you watch our first tutorial session for the motor protection. There I went a little bit more into detail in this. Here we use the same model, but we, of course, use different parameters, different input values, because it's a different thing what we want to protect the rotor and not the stator. Always the problem when we model such things, I already explained that in the first tutorial, is to get proper data from the motor manufacturer. All these models are estimations or approximations to the reality, to the real world. We could make them also more refined and more complex. However, then the data is just missing from the motor manufacturer. You don't get it, we don't get it. And if we have a model where we cannot feed this model with the right data, then it's not useful. Therefore, the compromise is to use such an equivalent model, as it's already also recommended here by this IC standard, as you can see here. So we based on that. The data we have from the motor manufacturer for the rotor is the number of cold starts or starts from the cold motor situation, the number of starts from the warm motor situation, so the motor is running for a longer time under nominal conditions, and then the starting time of the motor and the starting current. And all those four belong together. Means normally we get, or you get, the data. You have a starting time, a starting current, and for this, based on this setting or on this situation, you can start a motor so many times from cold and from warm start. So these four belong together. Okay, let's have a look. So from this equivalent model, we can get a differential equation, and this differential equation, when we solve this, I just left out a lot of steps. So again, in the first tutorial, you see how we come to these dimensionless values. Just maybe one word, this theta, what we see here, is dimensionless. And if this is 1, this is also what we show, 100% as a value on the display. This means the maximum temperature is reached for the stator and also here for the rotor. So I get such a differential equation here if I have a jump in the load, or a jump in the current in the end temperature, which is then going like an E function. You see here this E function. So basically I have a starting point and I have an end point, and in between I have an E function running between those two temperatures. The θ2 here is the end temperature, θ1 is the starting temperature. And now it depends, if θ2 is bigger than θ1, then I will have a rising E function. If θ2 is smaller than θ1, then I will have a temperature drop with an E function going down. For example, if the motor is running or starting and then you switch it off, then the temperature will go down. Then we have this falling E function here. Okay, Maximum temperature, as already said, is 1. Then we give the tripping command. Now we can assume that we get this maximum temperature if we start n times from the cold start times the starting time here. And then I get my maximum temperature. So 3 starts from cold bring me directly to the maximum temperature. This is one assumption from cold state, from warm state. It's a little bit more complex. I have n warm times starts from the warm situation, and you see here now the warm state is nothing else than theta n. That means the motor is running with a nominal current, and then I have a steady state temperature situation, and then I have the operating temperature or the warm state temperature of the rotor. So I'm talking only of the rotor, about the rotor here. Okay, and we can calculate this theta n. It's 1 over kr square. R indicates this is now the k factor for the rotor as a difference to the k factor which we discussed last tutorial for the stator. And the end temperature is basically what you see here, the starting current divided by k times In to the square. The temperature always goes with the square of the currents, roughly spoken. So the known quantities in those two equations are those which are marked here. These are the given data what we have, and the unknown quantities is basically this tau in this equation and this kr. We don't know that. We have just the 4 inputs as discussed before. But we see we have here 2 equations and 2 unknown quantities. Therefore, we can solve the whole system. And here is an approximation for those 2 values, this tau and the kr here. And then we have everything that we can calculate our temperature based on the quantities we measure and on the quantities we calculated here at the end. Okay, summary. The used thermal model allows to work only with a few settings, which we also get from the motor manufacturer. Again, doesn't make sense to set up more precise, more complex models, which we cannot serve because there is no information. And if I make NC starts from the cold motor status directly one after the other, then I come to the maximum temperature of the rotor. So N starts, which are allowed, will bring me to the maximum temperature. To have a little bit a better feeling what's going on, I just make a calculation example. I think a rather standard thing here. I have 3 times from cold, 2 times from warm starts allowed. And then I took 5 seconds starting time and 5 times nominal current is my starting current. And then we come to these quantities here. So I have a tau of 122 seconds. So this is a little bit more than 2 minutes. And you see here already, if you compare this with the time constant of the stator, this is much, much smaller. Therefore, we can also say only for a short time, when I put some current into the motor, the temperature goes up quite faster than for the stator because of this reduced tau here. And another finding is that my warm temperature or the temperature under nominal conditions is relatively small if you compare it to the values we discussed last time for the stator. There we were around 89%, for example. Here we have 1/3, and this is somehow clear if I think about I have 3 starts from cold and 2 from warm, so the difference is 1. And if we say, okay, approximately we get the same temperature rise for each start, then it's 1/3, and this is basically more or less 1/3. It's not exactly 1/3 because I have a bend here in the curve. The curve becomes flatter even here at the beginning, and this is this 1% difference here. And in the same way, we can say, okay, if 3 starts are allowed from cold and I do 2 starts, 1 more is allowed. So what is then the temperature? This is what I can also calculate. You see here the formula. And here I come to, where is it? 68%. So 2/3 roughly spoken. And 1/3 is then left over, a little bit less, to come to the end temperature for the 3 starts in a row. Okay, so I hope this makes a little bit clearer. And you see the end temperature is here. This is 8.6 times the maximum allowed temperature here, which is 1. And what we do here is, this is what happens during the start. So in this small range between 0 and 1, there we make the temperature supervision. Everything else goes far above that here. So it's a relatively fast and sensitive thing here. Okay, what comes next? Conclusion. Rotor is very sensitive for the high currents during startup. I have normally a relatively small time constant according to this model. So the temperature goes up very much faster than with a stator. And as a consequence, because we have different situations as well, we have various protection functions here. First is the restart inhibit function. This is against too often starts in a row for the motor. And with the motor starting supervision, time supervision, the ANSI 48. And this is against a too long start of the motor, which can happen, for example, if the load is too heavy, if the voltage is too low, so that the torque cannot be anymore created by the motor to start up the load, or if you have a locked rotor situation, that something happens in the machine and you want to start a motor and the rotor does not just start up at all. And then we have a third function which can be used as an option. This is the overload protection for the rotor using the thermal model as we discussed before. The restart inhibit uses this model as well. So we have two functions who are working with this thermal model. However, the restart inhibit function, restart inhibit function becomes active when you switch off the motor and prevents the restart that you can switch on the motor again. So there's a blocking signal, whereas the overload rotor protection function would trip as soon as the calculated rotor temperature becomes 1 here. So you can switch this on and then you have, let's say, a third function available. Thank you. Okay, before we go into the restart inhibit function and the other function, I need a little bit to prepare the situation because these functions depend on the status of the motor, if the motor is running, at standstill or starting. And therefore, we have some additional functions in this protection device, the so-called motor monitor, as you can see here on the left-hand side, which gives us the information in which state the motor is. Here on the right-hand side, you see the hierarchy tree. And here we see our motor function group. And in this motor function group, we see here there is one function called motor monitor. And I would like to talk a little bit about that first. This motor monitor, I have it here on the slide, evaluates the circuit breaker position via the current flow. So this function is located in the circuit breaker function group, and it borrows this information from that function group. And yeah, at the end, it is to understand, is the circuit breaker open or closed? Is the motor at standstill or not? Basically, we can say. We have a closure detection of the circuit breaker. This is when the motor is started at the beginning. And this motor monitor delivers me the motor state, so standstill, starting, or running. So we have here a motor state detection built in. Okay, let's first have a look on the current flow criterion. So these diagrams are all from the manual, so you'll find them there as well. So here an additional help to explain them here. I have here this I open signal. This means the circuit breaker is open based on the information with the currents I get. Basically, I have here the 3 currents that come in for each phase. And then I have a threshold. And if I undershoot this threshold in all 3 phases, then we can assume the circuit breaker is open. No, that's not correct. It must be in 1 phase only. So I was a little bit unsure here. Then we've built in a second functionality. This is when you switch off a fault, then you might have still a current which is relatively high, maybe higher than this threshold. And so not to delay this information that the circuit breaker is open already, with the second part of logic, and it just checks if the current has dropped below 10% of the current when this tripping command was issued. So it's a relative criterion, whereas here I have an absolute criterion, a threshold as such. And then here the function group or the function group circuit breaker or the protection device as such decides, okay, circuit breaker is open. So this is the open detection. Now let's have a look on the motor state detection. I have the state standstill. This is when the motor is at standstill. And I have the status starting. And I come from standstill to starting when the relay sees a current flowing which is higher than a certain threshold. So there must be a current bigger than a threshold, and this threshold is a setting. And if we exceed that setting, we assume the motor is starting. From starting, I can come back to standstill as well. If the circuit breaker is open, basically, this is the criterion we had before. So all the three phases must be below that threshold, and if all phases are below that threshold, then the circuit breaker is considered open, and then the motor goes to standstill. It can run still due to the mass of the rotor and the machine, but it will slow down and come to standstill. Then I have the running state of the motor, and I can come from starting to running if the current goes down again, because we assume the starting current is higher than the nominal current, the load current, which is there when the motor is running normally. So I fall below that threshold here, but it's not just that threshold, because the current goes down slightly and drops down. It must be below another threshold, and this is 1 times 2 the nominal current. Yeah. An additional criterion here is that the frequency is also the nominal frequency, or better, above a certain threshold. So we have a frequency threshold built in here, a setting. So if we are above this threshold, then we assume the motor is running, because if the motor is running, then we measure the currents, and the currents have the frequency of the grid, whatever that is. Okay, I can come from running to standstill, again, when all the three phases are open. So again, the current criterion we discussed before, of the frequency is smaller than a threshold. Okay, and then we have a path from standstill to running. So how can this be? For example, if the motor is already running and the relay is switched on, then the relay can detect, okay, the motor is running, because normally it will start up and wait and think the motor is at standstill. And if then there's current running, current measured, and the motor is running, then we can also come here from standstill to running. So this is the simple part of the whole topic here. We can have also dynamic situations, phenomena of the motor. So I have for example, a high-speed busbar transfer. Then I have a short interruption of the power supply of a motor, or even several motors. So there are different effects. And therefore, we have also slightly different additional criterion maybe, which we can handle with this model here. So I don't want to go there into detail, just to give you the basic idea. Another point is that we, at the moment, do a refining of this model. Therefore, I put the status as we have it or had it so far. In the future, this will be a little bit more. There will be probably another state called slowdown between the running and the standstill, so that we can handle dynamic situations even in a better way. Okay, but basically the idea is we have this state detection, this state model, and out of this state model we get also the status of the motor as signals, like standstill, starting, running. Good. This said, let's go one step further, now more towards the functional thermal replica of the rotor. It's also one of these functions which we cannot delete. This is always there. You find it here in our hierarchy tree here under motor and then thermal replica rotor. And yeah, the function is just a fixed function, so you cannot add or remove that function. It's always there. This calculates the temperature of the motor, or better, of the rotor. It determines if the motor is cold or warm, in a cold or warm state. We don't need that so much for the restart inhibit, but for the starting time supervision, then we will see how this works together. And this function also calculates the rotor restart limit of the motor. So the threshold, when the temperature is above this threshold, a restart is not allowed. If the temperature of the rotor falls below that threshold, then a start is allowed again. So this is calculated here in that thermal model. And it calculates also the motor restart time. That means if I'm above this temperature, how long does it take until I come back to this temperature level that the restart is allowed again? Okay, and we have one more function. This is the so-called equilibrium time. Also, this timer is managed or handled in this thermal replica rotor. Good, so that's a little bit the logic. Yeah, let's have a look into that. I can define if I should store this thermal replica in case of an auxiliary voltage failure, power supply failure or not. Then I have the already discussed settings, so the starting current, the starting time, and the number of warm and cold starts here. These are the settings. And here I have the signal, restart limit temperature is exceeded. So this is basically the blocking signal, what I have or use. And I get also the calculated rotor temperature as a percent value. So if you put that on the display on the screen, you will see what is the actual temperature of the rotor, the calculated temperature there, and also together with the signal we discussed before, the time until you can start again. I don't know if I see this here. The rotor temperature setting. I'm a little bit thinking why there is this sign here in. It's basically the status of the temperature. There is a setting, and according to the setting, then here I get the information. I have the warm or the cold status of the rotor of the motor. And this is the equilibrium time. So every time I switch off the motor comes to the standstill. And I have the possibility to make a waiting time so that the temperature in the rotor can a little bit distribute, balance out. It's also a setting. You can set this to 0, or the standard setting is 1 minute here, what we have. Okay. And then I have two factors. So basically the time constant is calculated from the data we see here in the relay. I have the possibility to slow down the cooling process by two factors. The one is the cooling down factor when the motor is running. And then I have a cooling down factor when the motor is at standstill. So this here is, if there is no additional data from the motor manufacturer, then maybe you can leave that at the default setting. The default setting is 2. This kind of additional security, just to wait, to give more time that the temperature goes down as compared with the temperature that rises when you start the motor. So when the current is there, the starting current is there. And then we have another factor here. This is when the motor is at standstill, assuming that then the ventilation is not there, that the power that can go outside of the rotor into the ambience is smaller, the power is smaller, so it takes a longer time for the cool down when the motor is at standstill. So also here we have a factor. We'll come later across that. I don't know by heart now what is this factor. Okay, so this function prevents from a restart of the motor if the rotor would exceed the permissible thermal limit due to the start. So it's a thing in advance. So we say, okay, we assume the next start will be one of these standard starts as we got this data from the motor manufacturer. And then when we start from that calculated temperature, then we will reach exactly the maximum temperature. That means the maximum number of starts if we do the starts 1 in a row. or if we are somewhere in between. This is basically the idea. What this function cannot do is to look into the future. If the start is longer than expected than the normal start, of course, we will exceed the maximum temperature. This is then an extraordinary situation. Okay, prevents from multiple starts and stops in a short time interval. So we have basically a thermal stage. This is the first sentence here. So I calculate what is the maximum temperature from which one I can still make one standard startup. Then sometimes there is other data from the motor manufacturer saying, okay, in a certain time, I'm allowed to start so and so many times the motor. And this we can then handle with a second function or second stage, a so-called counter stage, which then checks, do we make not more than, that we don't make more than X starts in a certain time interval. Okay. And then we have a third stage here, the timer stage. This ensures that a certain amount of time passes between two starts of a motor. So I think that's not correct, between stop and restart of the motor, between two starts of a motor. I have to correct that later. Okay, so this is the function as such. We see the thermal stage is always active. It comes per default if I add this function into my function scope. And the counter and time stage is optional. Okay. Again, this function does not trip. This function just prevents the restart inhibit, so a blocking signal, which prevents a restart. So this function becomes always active. The motor is after the motor has been switched off and the motor is at standstill here. Okay. Let's have a look in the thermal stage of the in the logic diagram of the thermal stage. Here at that point here at this end, the motor is at standstill, and here we see the temperatures from the thermal replica here. Now this is the other function we discussed before. So I exceed the temperature here basically, then this flip-flop here is set. And this flip-flop here goes through this OR gate and goes out here, so it gives this restart inhibit signal. So yeah, after the motor is switched off, now we have to see where this motor switched off is. Let me see if this is somewhere here. Yeah, motor switched off, standstill here. Now I got it. So here this is for the standstill. Okay, and then it goes through here. Okay, and of course I have the possibility here for an emergency start. That means if I have this situation, but I need absolutely to start the motor, I can give this binary input, and then this blocking is overwrite, or it's cancelled out at the end, so then I can start a motor here. Okay. I've also a warning signal here. This is the warning signal. This comes immediately when the temperature is over the restart limit temperature at the end. And yeah, here's one important thing. I've also this signal as an internal signal. So if I activate this link here, so automatic restart inhibit, if I set this to yes, then I activate this link here, and that means that the internal control of this device, of the protection device, is influenced directly. So I don't need to use this separate signal here and make a wiring somehow to inhibit or to block the closing command by the signal. This is automatically done inside. That means the closing command, if you try to close then the circuit breaker via the keypad, for example, in front of the relay, or also from remote, cannot happen then because it's blocked. And it will also permanently activate the tripping signal of the circuit breaker, also to prevent an additional feature to prevent the closing of the circuit breaker in that stage. If you don't want to have this, then just switch that off. Then you have this signal restart inhibit, and then you can work with this signal restart inhibit with then a wiring in that. Okay, then we have this equilibrium time here, and this blocks the restart always after standstill for a fixed time. Okay. Yeah, and then we have the minimum restart inhibit time. So this goes in parallel to this restart inhibit signal. That means whatever is longer blocks the closing command for the longer time. I have an example, a couple of examples where we see how this function works. Okay, so here we have an example for the 3 starts from 0. So full stress, the motor is started here until that point here. And yeah, maybe I first explain the diagram. So here, this is the temperature, this is the time axis. And here in the second diagram, you see the currents here and also the time axis. So in the first part until here, I have here the starting current, and the motor is running with a nominal current here for a certain time, and then the motor is switched off. And these are 3 cycles here in a row. And here I have the 2 signals, the restart inhibit signal and the warning signal. And here we calculate the temperature, and what we see now here is, or what is indicated is, that temperatures are not equally distributed in the rotor. So if you have a look on the rotor bar, then in the upper bar, the temperature is higher than in the lower bar or the lower bar end. So there's a range of temperatures. This does not pretty much bother us because this is all covered by the data we get from the motor manufacturer. The motor manufacturer says, okay, we can do 3 starts from cold, so we don't need to care what if there is a higher temperature or not. This is covered by the statement of the motor manufacturer. And what we do is basically that we now calculate our temperature so that I get the maximum temperature 1 after the 3 starts. So because it's 3 starts from cold, in that way it's scaled, let's say, or dimension the function, because we enter the data from which we get from the motor manufacturer. And of course, we do an approximation, as already said. We have here this black curve. This would be the curve which we calculate. These are all E functions, although you might not see it now here really in that diagram, but it's a starting E function and a falling E function here. Okay, let's go through that. What happens? So I have here 3 levels. So this would be then the level after the first restart. So when the motor is running permanently, I will come here to that level, because I have 2 starts from warm and 3 starts from cold. So the difference is exactly that temperature here, which is roughly, as already said, 33%, 34, if we have this condition here. Okay, what we do, we calculate the temperature, and then when the motor is running, then the high current is not there anymore, current drops down, and then also the temperature goes down. And when we switch off the motor here at that point, then this restart inhibit function comes into the game. And what we see here is this equilibrium time. This is a time, a setting, which is applied all the time when we switch off the motor. So it's a minimum time not to restart the motor, even if the temperature is not in a critical range here. And this is again, so to give the motor time to balance out the various temperatures here. So to make a kind of, balancing out, I think we can call that equilibrium time. Okay, and then I have a next startup, then I'm still below here, and then I can directly go to a startup, the third startup here. And here now we see there happened different things. When I cross this restart limit here, then this warning signal is active, and this stays until the calculated temperature drops again below this restart limit threshold. So this is not the maximum, again, the maximum temperature, it's just one start below the maximum temperature. Maybe we can say it in that way. And here it's also indicated we have this minimum restart inhibit time, which goes in parallel to the calculated temperature, this time here. And whatever is longer wins, so either this or the calculated time. In that case, here the calculated, how to say that? The calculated time, let's say, until we come back here is longer than the restart inhibit timer. So this is shorter, and this here elapses, but it's still there, the signal, until the temperature is below that restart inhibit temperature. Okay, here's another example. Here we go up again in that way. So we start and we switch off the motor directly after the starting. So a rather unlike case. So it's not running at all. Then we see every time we switch off the motor is at standstill. I get this restart inhibit blocking signal coming from this equilibrium time here. And okay, I move up here up to the maximum temperature, and from here on, from here on the motor is running, and then it's switched off. And you see at the moment the motor is switched off, then this restart inhibit signal comes here and blocks the close command at the end. And now you see in that case, this restart inhibit minimum timer is longer than the time we need to cross again here this temperature. So then this one wins. And yeah, this is then the time where the motor cannot be started. So because this minimum timer here is now longer. And you see the warning signal disappears exactly when we cross this line here, and the temperature is then again lower than the restart limit temperature. Okay, in that case, just to give you a little bit feeling of how this function works, in that case, yeah, the motor is running for a long time. So I cross this line here before the motor is switched off. Then I have just this equilibrium time blocking, and then nothing else happens. So I can restart the motor after this time again. Good. Here is a difference. I have the startups, and then the motor is switched off here at that point. So I do not reach really the maximum temperature. And then here the temperature goes slowly down. This goes down with a still stand time constant, so the time constant multiplied with a setting, with a factor. And yeah, it goes until that point that we have here the restart inhibit and the warning in the same way, because here we cross the line, and then the warning gets over, and also the restart inhibit function is reset, because we are far bigger than this minimum restart inhibit time here. Yeah, and then as a difference, here the motor is running. So when the motor is running, the restart inhibit function becomes not active in the way that it does not give the signal, the blocking signal. So then from here on, everything is in the safe situation. So when I switch off the motor later, then I just get again this equilibrium time blocking, if I want that, but nothing more. So then I can start the motor again. So I hope this gave you a little bit better insight how this function is working. And yeah, let's come to the counter stage, the second part of this function, the second stage. The counter stage allows a certain number of starts in a certain time period. That means if the maximum number of the starts is taking place, restart inhibit signal is issued until to the end of this time period. I have a diagram later, we see that. Let's make this example. I have a time interval of 60 minutes. That means in the 60 minutes, the motor can be started 2 times. This is what the motor manufacturer allows, but not more. So I have tried to prevent the restarting. If somebody wants to start more often in that time period. Let's assume I have the first start at 0 and stop after 10 minutes, and then I have a second start at 17 minutes and stop the motor after 33 minutes. Then this inhibit time will be 60 minutes minus 33, which is 27 minutes. That means from that point of time on, when the motor is switched off, is at standstill, in the standstill condition, then this blocking signal will be issued, and it will go 27 minutes long. I have it here on this diagram. So here the motor is started and stopped, started and stopped. The restart inhibit timer starts with the first starting, and these are our 60 minutes here. Yeah? And if I start it then for a second time, the motor, then my maximum number of starts is reached here until this restart inhibit timer elapses and everything resets. And beginning with the second stop, then this restart inhibit signal becomes active, because from here on another start is not allowed. only when this time here elapses, so after the 60 minutes after the first start here, basically, and then we have a new situation. So this is basically a relatively simple counter and a blocking signal to this counter. And yeah, you can use this always if you get additional information, like so and so many starts only in a certain time period, in an hour, for example. I think I go a little bit over that. You get the slides anyhow, you can read that. I've here some comments on that, just to go to the timer stage. The timer stage allows a restart of the motor only if the time span between a start and the next start, the restart, is bigger than a certain setting. So we have a minimum time between starts. If you have information from the motor data, you should wait so and so much time until you make the next start. Then you can activate this timer stage. Okay, example, first start at 0 minutes, then I stop at 12 minutes, and the second start is at 30 minutes, and I stop after 80 minutes, so always calculated from the initial start here. Then I will get this inhibit time, and this is then 25, because I have a minimum time between starts 25 minutes here. So I take the 25 minutes and subtract the 12 minutes, so there will be 13 minutes after that stopping of the motor until the motor can be started again. I have this also on a diagram, then maybe it's a little bit easier to understand. So the motor is running, this restart inhibit timer is activated, and this runs 25 minutes. And when the motor is switched off, then this restart inhibit signal here becomes active after 12 minutes. And then for this 13 minutes, as calculated before, this blocking signal is active. Here in the second example, the motor is running longer than this minimum timer. And then when we switch off the motor, this timer has already elapsed. And so there is no restart inhibit signal. And that's basically this part of the function. So we have a subdivision. We have 3 functions there. The thermal one, which is maybe the more complex one, and then 2 simple functions like a counter and a timer additionally. If you get data like that, then you can use those 2 additional functions or stages. They are implemented as stages in the relay. Okay, then we have this thermal overload protection for the rotor. As I said, this is an add-on function. It's not always used by the operators because it calculates very precisely the 100% and then gives a tripping command. So if you have a longer start and you come over the 100% value, then you will get a tripping, although maybe the motor is just at the end of starting. And if you want to avoid that, then switch that function off. If you say, okay, I want more safety here, I want then a tripping if the temperature, the calculated temperature is higher, then you can use this function. And basically it uses the same thermal model as the restart inhibit function, only that it gives a tripping command here. Okay, yeah, you see here, no. One slide back, I thought there is some animation here. No, simply you get here the rotor temperature, and if you exceed the 100%, this is the maximum temperature, then you see we get this operate signal. And yeah, we get this operate signal. This is our standard function construction we have with all our functions, with a setting operate and fault record blocked. And if this is set to yes, then the operate signal will not go out and there will be no fault recording. You just get here a warning signal. If you say no, then you want to have the tripping signal, and then you get here this operate signal, which goes into the function group circuit breaker, and there is created a tripping signal. Okay, as you already saw, now no secret anymore. We come to our question and answer session.
Yeah, the first block of it, and I've seen that there are already questions.
Okay.
I don't know how good your French is. I mean, mine is sufficient to read the question from AG that came in. J'aimerais savoir comment l'appareil fonctionne normalement. And I'm not sure if it means if the machine, if the motor is meant, how it works, if the protection device is meant, how it works. And I think the general stuff we already talked about in the first webinar. And so a kind of a really general question. So I guess, AG, if you need more information, contact Klaus directly.
Yeah, would be good because
it's a bit, yeah.
The English translation is basically, I would like to know.
Yeah.
Now it's
how
gone.
it works.
Now
yeah.
it's
fine.
The question is gone. How it works generally if the motor is under normal conditions. So how does the relay work if the motor is under normal condition? I don't know what to answer. It's not clear to me
well,
at
it's
the
just
moment.
silent, I guess, right? Let the motor do its work. All right, so we'll take the next one. Came in from AS, and thanks for your questions. So is there any current measurement from the differential CT or star point CT for the motor status?
Differential CT or star point CT for motor status? No. I think you referred to the differential protection where we have this window type CT and the cable goes through to the motor and backwards then. We don't use this current because this current is normally zero, ideally zero, so I cannot use that current. I use the normal current transformer that measures just the current that go into the motor for all these temperature calculations. So for the differential protection, this window type CT is on top of all the other stuff, just for this one function, for the differential protection function.
Okay, thanks. And then SK wants to know how the rotor temperature is calculated.
Yeah, this is basically what I tried to explain in a nutshell relatively fast. As I said, we get a couple of inputs from the motor manufacturer, again, number of cold and warm starts, and then the starting time and the starting current. And then from this, we make, based on this thermal model, which I introduced quickly, we calculate the temperature, basically.
And by now, we know pretty sure that this thermal model we have of the motor works pretty fine, right? And that we protect the assets rate.
Exactly, yeah, we use it for a long time, this method, the last 20 years.
Thanks.
So it should work.
And then FM wants to know, how long do we expect the starting to last in the circuit?
In the circuit?
It was a rather early question, I think.
So I don't know what you really exactly mean with circuit to last in the circuit. Basically, motor starting up can take from a couple of seconds, 4 or 5 seconds, something like that. But we can have also motor startings which are half a minute or even longer. Depends on the size of the motor, on the load. How big is the torque of the motor compared with the load torque, and that defines us how long the motor start is at the end. So it's a very extended period of time, can be from a couple of seconds to maybe a minute, I don't know. But I've seen already data. For example, if the voltage is lower, then you can have a prolonged starting time. Then I saw already data of 40 seconds or something like that.
Okay, and the next one is a rather special one. VM wants to know, how are settings calculated for commuter rolling stock traction motors? That's a special type of motors, right? Did you already work on that?
No,
experience.
I don't know exactly what that means. So we have to maybe come back, please, to me, and we can discuss, or you can explain me the situation better. So I'm really at a loss at the moment, sorry.
And I think now we have a redundant question, once again, about the rotor temperature, already answered based on the model. Then next question came in from WM. How is the rotor temperature techniques measured, as it is a floating mass internal the stator?
Okay, so we don't have a sensor in the rotor, something, maybe you mean that the rotor is rotating. We just, again, take the currents which go into the motor, the 3-phase currents, and with the data from the motor manufacturer, we build up this model, this thermal model, and this thermal model we use to estimate the temperature.
Thanks. And then the next question came in from AS. Is there any standard time gap between the starting time and the locked rotor thermal curve.
If this refers to the motor data, I can say from what I have seen as curves and data, there is not a standard time. I have examples later in the next session. We can have the situation that the starting time is shorter than the maximum locked rotor time. This is, let's say, the easy situation. We can also have the opposite, so that the startup time is longer than the locked rotor time. Then we have to add some additional features or measures that we can handle the situation here.
So it depends on the motor model, right?
Yeah, on the type of motor and how it's dimensioned.
Yeah. And next question came in from MK. What is the value of the maximum temperature you consider for the motor thermal protection? Is it considered the same as the insulation type?
So, insulation type. Last time we were talking about the stator thermal protection, overload protection. There I made a reference to this insulation type. Often you have this FB class, and from this, and also another value which we need, this is the temperature rise under normal conditions, under nominal conditions. We can calculate the over temperature, the allowed over temperature, or this K factor for the stator. Here we don't consider that at all, because we consider just the data we have from the motor manufacturers, the number of starts and the starting time and the starting current all together. With that, we build up our model for the rotor. And again, this rotor temperature model is completely independent of the stator temperature model.
Okay, thanks. And last question for this round of question. FJ states that the temperature is important and asks how much percentage is permitted as oversettings. Well, just roughly.
Oversettings.
Well, maybe something with current, or a voltage, probably not, but maybe over current. But I guess that's already dependent from the type of the motor, right?
We should ask the question again in detail, that I can understand. I don't understand the question at the moment. What is behind?
If you want an answer to this question, please try to make it a bit clearer to us here in the studio. I think now we'll go into a really short break. Yeah, get some fresh air in here. Give your ears and your eyes a bit of a rest. Yeah, take a sip of water or a glass of coffee, a cup of coffee, whatever fits you. And I think we'll meet again in about 6 minutes. Fine for you? Nodding there? Fine. So in about 6 minutes, let's meet back again here. Yes, we do have a short break, and we'll see. It could be that it stays silent now. We have a different configuration today, but we'll be back. Hello, welcome back. Thanks for all your questions you've placed so far, and please continue to do so. We will now have the second block with Klaus right here, continuing the journey around motor protection. And yes, please place your question, continue to place your questions in the questions to the speaker field, we will have at least one more question and answer round. So Klaus, let's continue.
Yeah, let's continue. Where are we here? Okay. Now we come to the motor starting time supervision. Gerd? Yeah. Can you take me out of the picture? Oh, so that's better for me. This was just a short internal communication here. Yeah, motor starting time supervision, as already said, this is to verify if a single motor start takes too long time compared to the restart inhibit function where we said, okay, we see that we don't make too many starts in a row. And it is more about abnormal long starts, what can happen if something goes is not okay at the end. Here I have again this example, rotor temperature example. Yeah, startup time 5 seconds, 3 times 5 seconds, and then the starting current 5 times nominal current. Then I will get, okay, after 15 seconds, then 3 times 5, I'm here. And then if it prolongs here the situation, then you would come to temperatures like that. You see here much too high temperatures. If we have a closer look here and zoom in, then we see this is rather like a straight. So it is a little bit bent already, this curve, but it's almost like a straight. And therefore we can simplify this function. It's straight because there's almost no heat dissipation in that short time here. The heat dissipation is significant at the end, so then the temperature does not go higher anymore, almost no higher. But here we can neglect this heat dissipation. And therefore we use a little bit simplified thermal model, a different one. This looks like that. And you see, it's again this single body model, but here you see there is a switch which is opened. So we don't care about heat that goes out of the model. I've just the power going in and the temperature rises here accordingly. Okay, the tripping time from that would be according to this formula for constant current, means I've again a couple of settings, the starting time and the starting current. And if my current, which I measure, is exactly the starting current, and the trip time will be the maximum starting time. So far, so good. If the current is smaller, then the tripping time becomes bigger. If the current is bigger, then the tripping time, the maximum allowed time, so the tripping time at the end becomes smaller in that way. We have a difference to the other model here. We need a starting condition, because even if this is a very, very small power that goes into this object, the temperature will rise and rise and rise because there is nothing going out. So this was this balance situation we saw before with this E function. This we don't have here, so we need a starting condition. We always say we start from 0 with this temperature, and only if a certain trigger is there, and the trigger is not written there. Motor state is starting there. It's written, this is the starting condition. That means the current is over the threshold which we set to come from standstill to the starting state of the motor at the end. Good. This is our curve, what we have, the tripping curve of this function. And yeah, let's have a look on the settings first here. I have here two curves, basically, one for the cold motor and one for the warm motor. So different maximum starting times or tripping times here. And what I now need to do basically is to get, again, a pair or a couple of settings, the starting time and the starting current that belongs to the starting time. And yeah, in that case, it is the maximum starting time which I need to enter, because the normal starting time, if I then would exceed the normal starting time a couple of %, then it would always trip. So here the idea is really to enter the maximum starting time. So after that time, then I must trip, because then I endanger the rotor here. And I have this the possibility to set two different starting times for the cold and for the warm motor here. The starting condition is the current threshold starting, as already mentioned. This is the setting which we have in the motor monitor. And you see if we are below, nothing happens. If we are above that value, then we assume we have the starting process. And then, here these two values apply at the end. So maximum starting time again means the maximum allowed starting time for a certain start current. So this we get also from the motor manufacturer is the data. Either there is a curve, I'll give you an example later, or it's a value which we have, and then we can enter this value here. It is not the standard starting time because this normally is much below the maximum startup time here. Additionally, we have a locked rotor characteristic. So this is this red one here. This locked rotor characteristic is activated via an input rotor locked. And if this input rotor locked is there, then I can cut down the tripping time here. So the idea behind this, if I know the rotor is locked, then I don't want to wait until the thermal limit, until the rotor already almost starts to melt, but then I can trip immediately then and fix the situation. Okay, the tripping time calculation here, as we do it here, considers also varying current. So if the current goes smaller or bigger, this is considered because we make a kind of integration for the temperature in order to consider it in a most proper way. So it's not just an inverse time curve and I go just there. So if I go here and then the current becomes bigger, then I cross this line and I trip. No, we make that in a little bit clever way to describe in a better way the temperature situation in that sense here. Good, this is different to the standard time. Quickly, the logic diagram here. We start always at 0 with the temperature calculation when the motor is starting here. Then I have here the two thermal images for the warm and the cold motor, depending on the status. Is the rotor state warm or cold? Then the one or the other one is applied. And yeah, if the maximum temperature has reached, then I go in here, the 2, and then I will have here at the end the operative signal. What else? In case of a locked rotor, here is the locked rotor time, the maximum locked rotor time, coming also from, this goes in as soon as there is the starting condition. And if the maximum locked rotor time has elapsed and the binary input is there, then I will trip immediately. So this is the locked rotor shortcut, what we have here. Okay. First situation, my maximum locked rotor time is bigger than the startup times. You see that here, it's a diagram from a certain motor here. And this is the startup curve over the time. So this is the time, this is the current. And then my startup curve goes here when I have nominal voltage. Then it goes like that. So it starts with 5 times nominal current. And then you see we come here to a certain value, which I cannot read now exactly in this small diagram. And if I have a reduced voltage, then the starting current is smaller, but the starting time is longer. So I end up here under 10 seconds, 8 or something like that here. Whereas this is the locked rotor time. So this is the maximum time which I can spend during the startup if the rotor is locked. And if it's not locked, if the motor is starting up, I have even more tolerance or leeway. That means I'm always on the safe side here. And in such a case, it's relatively simple what I could set as the maximum starting time. I assume, okay, I take just the locked rotor time, and maybe I subtract some time here as a tolerance, especially if the locked rotor time is relatively long compared with the starting time, then I can say, okay, I go somewhere in between, and then I'm always on the safe side here. So I take the starting current here from that diagram, then I look what are the locked rotor times, and then I go into that direction. So I subtract a little bit from these locked rotor times, and then I can set this as the maximum starting time. Now, so don't get confused. The maximum starting time is now equivalent, or we set it and orientate ourselves on the maximum or locked rotor time here. Yeah. Here I don't need a tachometer or speed meter because I know if the rotor is locked, I will be tripping shorter than the maximum locked rotor time, and when the motor is running, everything is fine. I don't need to distinguish these two states here. One word for the other setting point. So I can take either this one or this starting current and have a look here on the respective maximum locked rotor time. And if you do that with such kind of diagrams, you will find out, at least I found it out in many cases, that it follows exactly our tripping time calculation, which I explained before, based on this simplified thermal model. So the I square, I divided by I square function, that means if the current is smaller, then the tripping time is longer. And this curve here behaves relatively close to that formula. So this is a fine finding, and it shows it works here. Good. If I use a tachometer, if I have this already, then I can set this maximum locked rotor time, so it's one setting, to a relative short time, for example, 1 second. So I know, okay, now the rotor is locked, then I don't need to wait until the thermal reserve here of the motor is finished up. Yeah. On the one hand, this is less stress for the rotor. On the other hand, if I fix the problem and I want to restart, then I have still thermal reserve because I did not use up the complete thermal reserve by the locked rotor situation, but I switched off the motor in time relatively fast. So this could be two ideas to use a tachometer here. Nonetheless, it's not necessary here. Although it's not necessary. So here I have another example of a motor. Here the locked rotor thermal limit, this is this red curve here, so I enhance this by drawing this red curve here, is smaller than the start curve. You see here the starting time is like this value here, 2 seconds. No, these are 10 seconds, 20 seconds. You see this is a rather big motor. And the smaller the voltage is, the bigger is the starting time, and of course the smaller is the starting current. And we cross here this locked rotor limit, thermal limit. That means if the motor is running up, this curve here is allowed. If the motor is stalling, the rotor is locked, then I must switch off at that point latest here. And yeah, I cannot just take that value because it's always smaller than the starting time. So I need to distinguish here between the locked rotor situation and the normal starting. And therefore I need somehow a tachometer or speed meter to understand, is the rotor locked or not locked? If it's locked, then yeah, this time here applies, or I just immediately trip then. I could set here my locked rotor time to a certain value. Or if not, then I have a setting that allows me to make here the normal startup time. Okay, in that case, the setting for the maximum locked rotor time is short delay, or you use really the maximum here from this time diagram. Then you bring the motor to the thermal limit. And then you have to decide, is this reasonable? Does this make sense or not? Maybe it makes sense if you have the hope that the motor still starts after a couple of seconds when it's locked, that it starts anyhow, and then you can make a start. Or you say, okay, if I find out the rotor is not running, is not moving, then I trip in a relatively fast time here. Okay, now the question is, what are the settings for my starting time and the starting current here? So here we don't have, from this diagram, I don't see it really exactly. So I see what is the standard starting time, so I can take that value here. But if I'm a couple of milliseconds longer, then I would trip probably. So I need to give some margin in here. And for that, here you need again to contact the motor manufacturer. What is a reasonable value for the normal startup, the maximum normal startup time, if you don't have this? Or if not, then yeah, I would assume, but this is just a guess, yeah, that a little bit longer than the normal startup time can be still tolerated by the motor. Then the question is, what is a little bit longer? Maybe 10%. So here I cannot give you really a recommendation. What the recommendation is, ask the motor manufacturer what could be a proper setting for that value here. Okay, so in that case, we need a tachometer, a speed meter. This is mandatory in that case. This is, I think, the outcome of that slide at the end. Good. Then let's go to the negative sequence current protection. First, we can get negative sequence current if we lose one phase or one fuse here is blown or whatever. Then I can get an unsymmetrical voltage as we see it here. So this is one case, simplified case. And I get currents, positive and negative sequence currents here. No, sorry, these are the line currents, line B and C. And if you sum them up, then you get a picture like that. That means your current is flowing in and out here. And the current here on the line 1 or phase 1 here cancels out each other, those two here. And in that way, I just get here 0 current on the phase 1. Yes, and if you calculate the negative sequence current out of that, you get a relatively high value. So the problem is the motor is relatively sensitive. The rotor is sensitive to this negative sequence current when the rotor is running. Of course, when the motor is at standstill, then it will maybe go in the other direction. But when the rotor is running and turning in one direction, driven mainly by the positive sequence currents, and then you put a negative sequence current on top of that, then you have almost a double speed of the difference. The speed difference is almost twice the rotor speed. We can say it in that way, not very precisely, but basically like that. And if you look into the equivalent diagram of the motor, then you see for these negative sequence currents, you have a higher slip. Then we can say the slip is higher. It's 2 minus S. S for the positive sequence current, and this leads that I get a relatively high current in the rotor due to this negative sequence current. Okay, if you compare it to the positive sequence current. The other effect is if we have a voltage unbalance, then I get also negative sequence current. And here it is that relatively small negative sequence voltage creates us a relatively big negative sequence current. You see that here. These are kind of rule of thumb values. If you have a percent of U2 of negative sequence voltage, you get 5 to 6% of negative sequence current here. So it's a very sensitive thing. And this negative sequence current here, is a topic of the heating up of the rotor, a thermal thing. And therefore, we have also a thermal function behind that negative sequence current, which we call unbalanced load protection. So here we calculate also a temperature increase. Whereas in the case here, we have a simple definite time function. We measure the current, and after a certain time, we just trip because the current is that high, so that we don't want to let the motor run with this high number or high amount of negative sequence current here. Good. Also here with a thermal model, now you see it comes back and back. Also here, this switch is open. That means we don't have, let's say, we don't consider any heat dissipation. The negative sequence current comes, and if it remains for a certain time, then we will trip here. Also kind of simplified approach, and the tripping time here you see is equivalent to the starting time supervision, only that we have here the negative sequence current in the denominator. Here that means the bigger the negative sequence current, the smaller is the maximum allowed time, the smaller is the tripping time than here. For a constant current, of course, this applies only if the current goes back and forth, then the tripping time will vary. But we also consider this because we integrate up the time related to the negative sequence current here. Also here we need a starting condition. Here it's not like the starting current as we had it before with the starting time supervision. Here it is the maximum permissible negative sequence current. So this is a value you need to get from the motor manufacturer. And often you get a diagram which looks like that. You have the negative sequence current in per units. And here I have the maximum time which is allowed. And now we see here this red line, this is 10%, 10 to the minus 1. This is the line which is continuously allowed. So in that case, for this motor, 10% negative sequence current is always allowed permanently. So this would be our starting criterion here. Okay, what we then need to know is we need to scale now our function, and we need this K value, basically what we see here. So we have the negative current, negative sequence current. We need this K value here. And yeah, now let's come back to that formula. If you have a look at that formula, we see if I2 is equal to IN, so the negative sequence current is as big as the nominal current, then my K factor here is equivalent to the tripping time, the maximum tripping time. So what I do here in this characteristic now is, now it comes here, I search here, where do I have 1 as a negative sequence current? So negative sequence current equals the nominal current. This is 10 to the 0. And if I go along here and down, then I get here my tripping time. And this is 15 seconds here. And this is at the same time my K value here. Because if both values here are identical, then my K value equals the tripping time. Relatively simple. And you could also use other pairs here of settings. With that formula, you will come then to the same K value. So this is just that equation reorganized, and then you come again to 15 seconds, basically. This is following also our rule here for the tripping time. So also this here fits perfectly. With a cooling time here, also here we have a recommendation for this setting. It's this value here, I2 permanently, set it in here, then with the K we derive from here, then we get the cooling time. So it's also setting. It's a little bit to slow down the cooling process. So if the negative sequence current goes away, that we do not reset this thermal image immediately, but we let it cool down here. Okay. Tripping characteristics similar to the starting time supervision. Yeah, we have here a starting point, and this is the maximum continuously permitted I2 negative sequence current. If you don't have a value, take 8 or 10%. So this is what most of the motors can do. Better check that you get a proper value, of course, from the motor manufacturer. And then I have here this tripping characteristic according to the formula here. We built in here also a maximum value, a limit here, which is 10 times this value. So in that current range here, our thermal model is working. And if we cross that, then we keep that tripping time. This is basically to stabilize that function. If I have a short circuit somewhere that don't get very big temperatures at the end, yeah, to balance this out a little bit. Therefore, we have this. It's to avoid overfunction case of a short circuit fault, and also that it does not take infinite time. No, not infinite, but a very big time, that the temperature comes down again if the short circuit is gone, for example. Therefore, we also limit the model to 200%. So it is working in the, let's say, in the range of maximum 100%, but not more. So it's not a protection against short circuits here, basically. Therefore, we have these limits on the ends again. What you need to know is how to set this K factor, how to get this, and I explained this to you. It's the time is equivalent to the tripping time when the negative sequence current equals the nominal current of the motor. So we need to get somehow a data which is this one or a related one. We can calculate that. Okay, I will jump over the logic diagram. I leave it here in the slides. You can download the slides later. You get some additional comments on my side so that I can come to the next point, which is the load jam protection. This protects the motor in case of a sudden rotor locking or jump in the load. Something gets blocked, stuck, or something like that. And we can see this because then the current of the motor increases simply. We have a jump in the current, and what is important, of course, during the startup, we have also kind of jump of the current. We must be sure that this function does not work during the startup of the motor. Therefore, this is active only when the motor is running. So again, you see here our state model. When the motor is running, this function becomes active. When the motor is starting, the startup supervision becomes active or becomes started. And when the motor is at standstill, again, the restart inhibit function becomes active with the meaning that it blocks the close command. So it will be calculate, will always be active in the background and calculate, but this is then the effect what we have. Okay. We could work also without, or live also without that function, then the overload of the stator rotor will give a tripping command depending on how big the current is. But this is a slow function, and this can take a relatively long time. And to cut down this time, we have this load jam protection. So if the motor is running, then we want to trip the motor. If there is some blocking condition, then you want to trip that motor relatively fast and not wait for half a minute, 1 minute, 10 minutes, whatever, for the thermal overload protection. Okay, it's one function. And basically, what happens is, if the load increases of the motor, also the torque increases is what we see here, and the current increases. So when we have here our nominal working point, and then I get a stronger load or something gets somehow jammed, blocked, then the slip will go up, so the speed will go down of the motor, the torque will go up, and together with that also the current will go up. And this is basically what we detect or what we use. We look if the current goes over a certain threshold, basically. So if the required torque is higher than this stall torque, or it's like a break-even point, then the motor will slow down at the end. So this is just to explain a little bit this diagram here. I have another diagram. This is now the various quantities here: speed, mechanical load, and the current. And this is the time axis. So if I have this locked or a jam situation, not a locked rotor, but a jam situation, then I will see from there on the current will increase. And if it goes over the stability limit here over this current, then I can be the current, okay, this is this current here, which I get for the maximum torque, then I can be pretty sure that the motor will come to a still stand here. The mechanical load goes up and the speed goes down to 0 if I go really over that value here, the maximum torque. Okay, what do we do? Now a logic diagram. Motor must be in the running state, as already said, because otherwise I will trip on the starting current. This is not okay. This is not what we want. Additionally, I have here a release delay timer. That means if the motor is in the running state, why not give a couple of seconds here on top of that, just to be sure that everything is running smoothly, and then activate the function here. So this is to activate the function here. It goes here into this end. Okay, so I have two thresholds, a warning and an operate threshold here. And yeah, I measure the positive sequence current here, and this works on the positive sequence current, those two thresholds. And here I have to pick up an operate signal. So if I exceed here these values, especially the operate value, then I go into this AND gate. And after this release delay timer has elapsed, then this AND gate becomes 1 here. The output, I get a pickup and also the operate signal here. So that's basically, I think, all for this load jam protection. Good. I would like to go through an example, setting example of one motor. I think I took kind of typical motor here and go through the settings so that we get the complete picture here again, and based on some practical data here. So I have, I think, 4 data sheets. I hope you can see that on your screen. It's a little bit small. yeah, I get here some general data like the power 1370 kilowatts, 6 kV, 50 hertz, and the current then is 154 amps, the nominal current here. Thermal class FB, so this gives us an indication for the stator overload protection. Then the locked rotor current, here you see we have this data. When the voltage is the nominal voltage, then I have here 5.65 times. And if the voltage is 70%, then I have 3.9 times nominal current. This is my locked rotor current. Okay, the locked rotor time here is 13 and 9 seconds. So for cold and for warm. But now we need to understand what is the startup current, or the startup time better. Startup time. So I have another diagram here in my collection of technical data for this motor. And this is the startup curve, basically. Here is the slip. Here it's 1, so then there will be no current at all. And somewhere here I will have the nominal slip and the nominal conditions. And here I have the current over the slip. So this does not give me an indication for the time, but from here I also could get the startup currents. It's always the current at the beginning of the startup. This is the current which we call the starting current here, on which we base everything. So here's a diagram with the torques and with the mechanical torque. So the machine, oops, this was one too much. The mechanical torque, and you see the mechanical torque which is required by the driven machine is smaller than the torque of the motor. Therefore, the motor will start up here. And here I have an indication about the starting time, 3 seconds and 10 seconds. And if you remember what are our locked rotor times, we see the locked rotor times are longer than the starting times. That means good. We can use the locked rotor times and we will be always on the safe side here. So we don't need a speed meter in that case here. So it's the first case we discussed before. Good. What else? Technical data. Yeah. Okay, these are the locked rotor times. So sometimes you have a curve like that. And from this curve, you can now go here to the starting time, starting current 5.65 and go up and get here the locked rotor times from such a diagram here. Okay, again, you can also take another starting current with a reduced voltage and then see what are the locked rotor time. Again, this can be recalculated by the formula we discussed before. What is interesting is that I get a thermal time constant of 25 minutes. This is for the stator, so that's an indication for the stator. Sometimes there is a smaller one. For the stator overload protection, we need to take the bigger one here. And then there's one, if the motor is not running at standstill, then you see this is much higher than the cooling down time is bigger than time, or the time constant is much bigger than the time constant when the motor is running, because the ventilation is missing here. Okay, good. Setting for currents and voltage inputs. So we have here the setting CT phases, and here you can select, I took 200 amps as a current transformer because my nominal current is 154 amps. So rule which is often applied is that the current transformer is slightly higher. The value is slightly higher than the nominal current of the motor here. Then I have a little bit more performance when we talk about short circuit. So this is the tendency that you do it in that way. I have here a setting for the start point direction in direction of the object. This is the motor in that case, yes. So that means my start point of the current transformers is in the direction of the motor here. And then for the settings for the voltage transformers, I put here 6 kV and the secondary voltage, whatever it is. In our case, I use the 100 volt, which is very common here in Central Europe. I would say 100, 110 volts. And we see those two entries for the settings here in the power system. So I have here the settings, this is my tree. Here's the power system, and then I have the measurement point, current voltages. There I have to enter these settings here. Okay, So next step, what I would do is to enter the rated values of the motor data, and we find this here in the motor function group under general. There we have the rated current and the rated voltage of the motor, and here the Dixie program calculates then the apparent power. Okay, then the motor monitor. Now here we discuss about the state detection. So it's the help for the motor monitor to find out is the motor running or standstill or starting. I have a current threshold for the starting. So there I need to understand what is my starting current, and now I have to consider the complete range here. Okay, this is the range which comes from the motor manufacturer. I have a starting current for 70% of the nominal voltage. Now it depends if you have such a voltage or not, or what is your minimum expected voltage where your motor must start, and you should orientate on that. So I took here the complete range, 3.9, because there's enough space towards the nominal current, or the, let's say, what I assume is the maximum load current of this motor ever. And this is maybe 10, 20%, 10% above the nominal current, not more because of the K-factor situation, class F and B, this discussion. So we get K-factors around 1.1, 1.15 maybe for motors. So I have enough space to that, 3.9 to 1.2. So I take something in the middle, 2.5. This should be fine because here I'm far away from any overload situation of the motor as such. Then I put here frequency. This we need to understand if we have dynamic situations like short interruption of the voltage because something is reorganized in the substation. The motor runs down and runs up again. And we detect that the motor runs down by this frequency here. So if we go with the frequency, the measured frequency below that value, then the system knows it's no longer running, the motor is no longer running. This has the consequence for the load jam protection that with a restarting current, the load jam protection is not activated here, which would be the case if you don't leave the running state. So therefore we have such a frequency. And with a current threshold for the running motor, which is, I took here the smallest value, it's 0.4 times nominal current. If the current is bigger than that, then we consider the motor is running here. Then in the function group circuit breaker, I put here also the rated nominal current of the motor. You can discuss if you put here the current transformer value, the 200 amps. It's a little bit philosophy, I would say here, and the rated voltage. What is important is this current threshold CB open value, and I put here a relatively small value, 5% roughly, of the, no, not roughly, exactly of the current transformer, which is a value which is fine. So even if the motor would be under no load, I would detect is the motor running or is it open, because the no load current of a motor is, in my case here, and often in that range, so more than 10%, 10, 15, 20%, something like that. So with a 5%, I can even distinguish between a motor running without load and an open circuit breaker here. This is all just one example, and I explain you a little bit the background, what I thought, so what we thought when we discussed these settings here. Of course, you cannot blindly adapt this to any other situation. So just do not take these values and put it into your situation. You need to think about maybe other influencing factors here. So I tell you here just a little bit my ideas behind the settings here, which I selected. Stator overload protection. So here I get this from the technical data, and this is out of the curve. Let's go back here a little bit. Yeah, this curve here. If you go and see what is here, the permanently allowed temperature here, current, then you come here to a value of 1.15. So you just need to measure that, or you get it as a value from the motor manufacturer. This is my K factor here for the stator overload protection. So now we talk about a function which we treated in the first tutorial here. If you want to know more about that and you missed the first part, then please go there and have a look in the first part. There we explained all these settings. The thermal warning here, I leave at 90% because with 1.15 as a K factor, I come to a nominal, to the temperature for nominal current with only 76%. So there is already a quite big gap to the 90% before I issue the warning here. Then my time constant, it's the 25 minutes and the 175 minutes coming also from the technical data sheet. And yeah, then we have a setting limiting current for this thermal image. Again, here is the idea, if I have a short circuit or a prolonged starting, I don't want to trip the starting with this function here. The functions work independently of each other. And it might happen that if I get a very high current here, that I drive up here the temperature too high. Again, this is all an approximation, the thermal models, because we don't get it more clearer from the motor manufacturer. Therefore, this might tend to overshoot, and therefore to say I take a limit current for this model for the temperature calculation, which is around the starting current of the motor, I think is a good approximation. Then we use the, not the starting current is threshold, which is under the starting current. So we have a kind of balancing out the temperature rise, because I want somehow to get temperature part of this starting current, but I don't want to have it too much. So it's kind of compromise here. And this default temperature, again, is the maximum ambient temperature I expect. So depending on what is your situation, you can leave this at 40 degrees. If it's hotter, then you set here the other temperature in degrees Celsius or Fahrenheit. So the rotor, thermal rotor replica here, permissible number of warm cold starts. Then I have here the tau factor extension factors here, the tau extension factors. The tau at standstill is 5 times higher, and if the motor is running and the cooling phase, then I also delay the cooling process by the factor of 2 here in that example here. Then I have the starting time and the starting current. So those two belong together with the number of warm and cold starts. So let's have a look on the technical data again. So I have to jump back again a little bit. Now the animation comes here. Somewhere I have an indication. Here it is. Permissible number of starts, 3 cold, 2 warm, for the nominal voltage, and also for a voltage which is 70% of the nominal voltage, so for the under voltage situation. If you make a little bit more calculations about the temperatures, then you will see it is a higher stress if you have the starts with a reduced voltage. The starting current is not that big, but the starting time is longer, and the starting time counts more in these calculations. That means if you want to use really the complete performance of the motor, you should go for these values at 70%. So that means in our case here, where are we? Once more here and one more here, the rotor. I take here the 3.9, not the 5.65, and take the 10 seconds instead of the 3 seconds, I think it was, for the starting time. That means if you then start up this motor 3 times from cold state within normal voltage, then you will not reach the limit 1 temperature maximum limit, because it's a faster startup with less stress for the rotor. So you have more margin, more leeway for the starting up of the motor. And you can do this if the motor manufacturer states you that you have also these 3 and 2 starts, number of starts for the reduced voltage, for example. Okay, so then I have here a temperature threshold cold motor, warm motor. I don't set this to the 34%, which is our temperature for the warm motor, as we saw at the beginning. I set it lower because if I'm in the cold motor state, then I will apply the longer starting time for the starting time supervision function. So this has nothing to do with the restart inhibit for the starting time supervision. And in order not to take the longer cold motor time, if I have just maybe 33% or 32%, I set this to a lower value. So it's a compromise when to apply the shorter time for the warm motor, the maximum locked rotor time, and when I take the longer time here. So I go away from the 34. If I set this to 0, then I will always apply the warm motor time. So this will be then also always be warm. Then I have the shorter time. So here I make the compromise going down with this threshold between 34% and 0, somewhere in the middle. Okay. Yeah, restart inhibit. There's not much to set. You can set the mode on and you can set the minimum restart inhibit time, because this function takes everything from the thermal replica of the rotor. Yeah, and here I made one example. So I have 3 starts in a row and I come exactly here to 1, and then I let the motor cool down. And yeah, here's a formula how to calculate the time from here going down to there. And this could be an orientation for the setting at the end. Or you say, okay, I trust the model and I make this a short time, couple of minutes only. Okay, starting time supervision. Here I use 2 settings, 2 timers, one for the cold motor and one for the warm motor. And I get here the values for cold and warm motor for my starting current with 5.65 times current. That means under the voltage conditions. I could take also the other one, then I get other values here. It's equivalent here because this curve follows, let's say, the calculation example, the calculation formula I gave you beforehand. So what I did here, instead of 13 seconds, I put 12 seconds. Instead of 9, I put 8 seconds here. So I'm a little bit shorter than the maximum locked rotor time, entering here my maximum startup current time here. And of course, the startup current as such, 5.65 times nominal current, is what I put in here. And yeah, maximum locked rotor time. In that example, I took 8 seconds, which is a little bit smaller than these 9 seconds again, just to be on the safe side, because I don't have a locked rotor tachometer connected, so this has no meaning, this value, just not to interfere. If I had a tachometer, I could set this to a lower value to make a shorter or a faster tripping, not to wait until the motor has heated up completely here. Okay, unbalanced load protection. So there is no data available. So I take here a maximum continuously permitted I2, the 10%, which is a common value, or 8%. And for the K factor, 2 seconds. That means if I have really 100% negative sequence current, then I would like to trip after 2 seconds here. It's a relatively conservative value if you compare it with the diagram we had before. There were 15 seconds. So this is up to you to find the right value here. Okay, then the negative sequence overcurrent protection. Here I take a threshold of 40%. The negative sequence current is normally much above this value. If I have an open phase, we talk about open phase here. And then I put here an operate delay of a couple of seconds. So here 3 seconds. I don't need to be very quick. I need to be quick, but I don't want to interfere with some transient stuff which can happen if some switching is going on in the substation here. Okay, load jam protection. I set here the warning threshold to 1.3 times nominal current and the tripping threshold at 2 times nominal current, because then I would say, okay, if it's more than 2 times for a longer time, then I have a load jam situation. Definitely I can trip. I don't want to continue in that way and wait. And here I have this release delay, 5 seconds. It's an additional safety before I activate this function after the motor is in the running state. Okay, I've also an operate delay of this load jam protection. Here I need to be careful or think about that with this motor, I could also feed an external fault backwards. So then the motor is running shortly as a generator and brings the fault current into that fault. And I don't want to trip on this fault. So therefore I put in here also a short delay time. So don't set here maybe 0 seconds, then you would immediately react on an external fault probably, if you don't want that. Overcurrent protection, so this is a repetition of the first session we had here. Here I go to 1.3 times that transient starting current, maximum transient starting current. So here all values are in primary values, so not to confuse too much. And I use an operator delay of 0, and I take a second stage, which I take with a certain margin above the, let's say, static, the long-term starting current, 20% of that. Here I use the fundamental component, whereas here I use the RMS value. This here is to compensate some saturation effects, which could make the current smaller. And this here is to filter out any DC component, which could give me also a wrong image about the starting current here. And the operator delay here important, a certain delay time to let pass this peak inrush current for which this stage here is responsible at the end. For the ground protection, I did not go into detail. This can be a complete separate discussion here. If we have a compensated or isolated network, I simply made here a second for the a setting for grounded network here. And yeah, I took here 0.2. During commissioning, you can check what is, maybe make a fault record and see what ground current comes out due to the unbalance of the current transformers, errors of the current transformers. When you start up the motor, maybe you can set this more sensitive, maybe to 10% of the nominal current, depending how you measure the current also, and then also a certain operator delay, also a little bit longer to stabilize this. Then the voltage protection. Here we did not talk about that, but I just put it here into the slides that we have a complete picture here. Here I said, okay, if I have 90% nominal voltage, then I will issue a warning after 10 seconds. And yeah, I can use also a second stage here, set this to a lower value. For example, if I have more motors and I want to, in case of a fault or so, or a problem with the in-feed, and I need to restart many motors, then I could make this restarting sequentially. So I start manually the first motors, then the next motors, and so on. And to trip the motors before I start them, I can use here just a simple undervoltage threshold, and I put this here to 80% of the nominal current, which then trips after some time delay, so that I can restart all the motors in a certain order. Yeah. Okay, then we are through with that part here, and maybe there are some questions on your side.
Yes, there are.
Okay.
I've already seen some. Klaus, thank you so far. And I think we need a bit help from the regie so that we see the questions.
Yeah, exactly.
Thank you very much. So, and we stay with this chronological order of answering. So RA wants to know, is there any available application for continuous offline earth fault monitoring for high voltage motors? The earth fault monitoring should automatically initiate a stop and a blocking on restarting until the fault is cleared.
I need to read that again.
Yes.
The available application continues offline. I'm a little bit struggling with offline earth fault monitoring, what the meaning is, what is online, what is offline. Okay, basically we can do anything with the Ciprotec 5 relays. I shall continue now. We have some issues here.
It's just my microphone that
okay, I see.
will not work today.
Okay. maybe we should also discuss this
So a
together.
question and a one-on-one discussion
I would say
help, right?
Basically, we can do a lot with stages with our CFC. A dedicated built-in function that looks like that, I don't see at the moment that we have that. But maybe we can have a talk together, and then I can better understand what you mean, what you want here.
All right. And then MK has a question for the thermal model we have of the motor. Do you consider the effect of an external cooling, for example, with a fan, into the thermal image?
Yes, this we do. We have different time constants for the running and for the standstill motor for the stator temperature and also for the rotor temperature. The rotor temperature is a factor which we have there, and in the stator overload protection, we have two settings, two time constants, and with that we can consider that.
Oh, perfect. Thank you.
So if you have permanently a cooling, so an external cooling which is not connected to the rotor movement, then you can assume you have the same time constants for starting up and starting or for the standstill, because the cooling effect is the same. Or maybe it's a little bit less, then you can also adapt this with the different time constants.
Thank you. Really helpful. And then next question also from MK. When the locked rotor time is less than the starting time, the tachometer signal is required. Is this a digital signal or an analog signal?
So at the moment we have a binary input. It's a digital signal, which we then, when the binary input is activated, then this additional locked rotor definite time stage is active, and then I trip after the set time, what I have there.
All right. And then next question seems a bit incomplete. Since the came in from AS, let's see if we can take it. Since the motor is allowed to start at 70% of the nominal voltage, then 27
under voltage function.
Under voltage function. How will this function or be set at?
Yeah, I see the contradiction. So if you really start with the 70%, then this under voltage function with this couple of seconds delay time will trip probably that it does not make sense. So then you should set this lower. This was more an example. At that point I went a little bit away from that, from the technical data.
All right. So it was just to showcase how it works and not necessarily a correct configuration. All right. Thanks for the clarification. That's also a helpful question there. And one fresh question came just in. If the motor is operated by
variable frequency drive.
Frequency drives.
VFD.
What function do you think are a must in the C-Protect relay on the switchgear?
This basically depends on on what the VFD provides as protection functions. So I cannot give here a general answer. If all the functions are already there in this VFD, then you don't need the protection device. If it's a big motor, maybe the differential protection, if it's not part of the VFD, what I could imagine, could be then a dedicated protection function for the C-Protect device. But all these functions we saw are more for the application without VFD. So if you don't have a VFD, variable frequency drive, so you switch on the motor directly on the bus bar, then all these functions come into the game, and you should consider them.
All right, thanks.
Okay.
And another kind of last question. The under voltage settings will be enabled after start of the motor, I guess. So the undervolt does not interfere with the
same story.
That's
in that case, it would interfere. I can see that point.
Yeah. I mean, that's an additional kind of answer information to the question we already had. Exactly. So that's so far for now, the blog with the questions. And we are running out of time, but yes, Klaus, if I understood you correctly, you are not running out of topics, right?
That's the point. So I prepared a little bit more. Okay, now I know the time is over, but if you're interested, I will show you one more feature, which is related to the motor protection, the startup log we have.
Mhm.
It's a kind of fault record which we can set up and have a look on that. And then we have some additional tools around CProtect 5, like the digital twin, the web UI, the web user interface, and the so-called CProtect tools, additional small tiny program, which I would shortly present after the break. So if you like, stay tuned, have a look there. If not, if the time is over, then maybe you have the chance to visit or to see the rest in the video, because this is recorded, and with the recording, then you can go there and watch the rest here afterwards.
That's
okay.
true. So another short break for you. It's okay if you leave us. We appreciate if you stay with us. And so we'll see you in a few minutes with the last block. Then it's the last one, right,
That's
Klaus?
definitely
The last block in this motor protection tutorials. And I hope that you'll stay in the line, get some fresh air, and we'll be back in a few minutes.
Okay.
Gut. Ja, Ziegelwiegel. Das Einsalmer, ne? Aber dann ist das jetzt aufziehen. Dadurch, dass du es halt frei ja, das ist hier wieder. So könnte man es sagen.
Verstehen, was da alles drin ist. Ich bin ja nicht in anderen Produkten, den Akku schon irgendwie steht, würde ich nicht erreichen. Aber ich finde es nicht, weil ich den Druckers teile.
Nein. Hier nehmen wir das.
Eben Möbel schon, Möbel, das wie vom Bordstein kam, zack, da stehen.
Ja, genau, hier stehen deine Sofas.
Das ist so immer wieder mal, das ist ganz. Ja, was Motorisierung kann. Das macht es da. Die ganzen Monitore, der ganze Stunde auf die beiden Platz einstellen. Das ist cool. Aber ich meine, das ist nicht ohne oder andere. Der Nachteil ist halt jetzt selber nicht ausstellen und vorher mal durchstoppen.
Hast du das Coach? Und das gibt nur eine Telefonwerbung?
Ja.
Das ist das meine. Ja, das ist total viel los davon. Soll ich da auch noch hingehen? Ich muss immer noch meine neue Installation machen.
Ja, mein PC ist auch nicht so zwischendurch. Ja.
Entschuldigung.
Ich erinnere, ich stand jetzt gar nicht gleich mal. Das hängt jetzt schon, ich mache jetzt das weg und starte also.
Okay. Stimmt, läuft nicht.
So, jetzt das Mikro mal an und dann kannst du starten.
All right, welcome back to the last part for today. As we already mentioned, more information that our expert will likes to share with you than we calculated time for. So thank you for all of you that still stay in the line. And now, Klaus, let's just continue right away.
Without a lot of words, let's go into the last part, additional functions and tools. Let's start with a startup recorder. So it's a built-in function now in the motor protection. And what do? We record the startup phase of the motors. What can we record? Currents, voltages, power binary signals like the circuit breaker, close command, status of the motor, and. This is a flexible thing because it is based on the standard slow scan recorder function, which we have implemented in all Protect 5 relays now above other standard functions coming from the fault recorder device 7KE8. So all the Protect 5 relays have now this slow scan recorder function, and we profit from this function because we use it for the motor start log. It's freely programmable, and it's a standard COMTRADE format or also a native format. And therefore you can see that with the SIGRA, the special tool belonging to Dixie, to show and analyze fault records, the COMTRADE viewer, Siemens COMTRADE viewer, but also with our web UI, web user interface, which is built in the relays, or any other COMTRADE viewer. Okay, what do we have assigned? So this is a part of our assignment matrix here, information routing matrix. The state of the motor, standstill, starting, running, the voltages, phase to ground voltages, and the current phase voltages, and also the close command of the circuit breaker. And so you see here XT, the T is the trigger condition. So this is our standard setting. If the circuit breaker is closed, if there is the close command, then we start this record here, this motor start record. These are the settings here, pretty much like an ordinary fault record, you know, from protection relays. Maybe one thing, the averaging time in cycles, that means we do not record samples, sampled measured values, but we record measurement values, which we calculate from the sampled measured values. And the cycle number here is basically the time frame which we use, the time period which we use to calculate a measurement value. That means the bigger this value is, the longer this time frame is, the longer is the averaging time for this measurement value. And yeah, the less values we get in a certain time, of course. Yeah, if we set this to only one cycle, for example, then we would get a measurement value every 20 milliseconds or 16.6 milliseconds here. Okay, and depending on this averaging time and yeah, the maximum time, maximum record time, we have also the estimated record number of records which we can store, so number of motor starts in that case here. Okay, this is how it looks like when you watch such a start record with the C graph, for example. Then I have here the voltages. One voltage is now missing because I wanted to show here also the binary traces and the 3 currents. And this is a special switch over of a motor here, which I had as a COMTRID file, which I run on the digital twin. And then I started this to create here this motor start record because I don't have a motor next to my desk. So I have to do this trick here at the end. And here you can see the starting currents and also binary signals for the startup of the motor. And you can maybe compare this with a record you had a couple of years ago or so and see if something changes in the motor. So just to register or see the behavior of the motor starting here. So the next tool is ZebraTech Web UI. The Web UI is a built-in server functionality in every ZebraTech 5 device. That means your contact device via the USB interface or any Ethernet interface, and you get the contact, you make the contact with an ordinary browser of your PC, so Firefox or Chrome normally, or Edge, maybe Microsoft Edge. And yeah, the key features here is this is always on board because this comes from the protection relay. What we can see are status logs, fault records, statistics. We can show and change settings in the relay. Yeah, diagnosis and overview of inactive functions. So this gives you a fast overview what is not active in the relay. And yeah, you connect in a safe way via encrypted HTTPS protocol, so either with a password or also with a role-based access control if this is set up. Okay, this is how the starting or landing page looks like. So we have a lot of tiles here for the various functions, and then you click on the tile, you get another view of tiles, so in a structured way. And in that way, you can navigate through all the functions. I just put some of them here on the screen. First is that we can show the screen of the relay and add additionally here alarms, which we define in the Dixie 5, which we can acknowledge. Here, for example, I made the example, I run over the restart inhibit temperature, and now this alarm is red because this signal is active, motor switched off, you see, and this remains red until the temperature goes, the calculated temperature goes under the restart limit temperature, then this becomes green, and then I can acknowledge this signal, and then it becomes gray. So here, possibility of having alarms which you can acknowledge. Settings, one picture of the settings. So you navigate here through the tiles menu, also via this menu here to the various sub-menus of the settings. Now here I'm in the motor stator, thermoreplica motor, so I can change here settings. Then I can click here or here and then navigate to other points where I have settings. And if all this is done, then I can click here on that button, and then I will download all the settings into the relay. Here's an example for showing measurements. On the one hand, we have here the measurements in a table form as real values. And also there's a possibility to get vector diagrams where there are vector diagrams. So for example, here for the fundamental components as such. In real time, of course, the vector diagram changes if the injected currents and voltages change. Here's an example for a fault record. So keep in mind, this all comes from the protection relay as such. So it's not an extra program. I can show fault records. I can get them first, then I can show them. I can trigger fault records even, so that there is nothing, then I make a trigger and then I have a look, okay, what is going on there. And of course, I can store these fault records on the PC. And the analyze possibilities here are, of course, less than with a SIGRA. SIGRA is a dedicated program to analyze fault records. Here I've basically just a time view. So I see the analog signals and also the binary signals, and I can zoom in, zoom out and scale that a little bit, but I don't have the additional editors like circle diagrams or so. Good. Last program is cProtect Tools that helps during the installation or cubicle mounting and also commissioning mainly. So this is the focus. This is now not a built-in functionality in the relay. This is a small portable program which you can put on every PC, and you just start this and you connect then also to the relay, and you have some additional features. For example, we have here a hardware and wiring test feature during cubicle manufacturing. You can upload configurations, firmware, or upgrade the device functionality, so add function points into the relay, or also now latest development, download device data from the device, the configuration of the relay onto the local PC where this program is running. So we see that again. So I load data via the cProtect tools into the relay, either via direct, or it's also possible to establish a remote connection. And the data I can load to the relay is the DAF file. So this contains basically the function points, the device functionality if I want to upgrade the device. I can load a certain firmware into the device, and also a configuration. GCF is a file which is created by the Dixie5, which contains a configuration for a device, which I then can download into the device without having the Dixie. So the idea is to give some persons tools to contact the relay, to program the relay, without the need of having the Dixie. The Dixie is the engineering tool, the complete engineering tool, which is very mighty, but which I don't need for simple tasks like downloading a configuration into the relay, for example. So here's a little bit the relation between the various tools. The tool does not replace the Dixie5. It's an add-on, I would say, for certain purposes. Okay, very quickly, I can show here binary inputs, which binary inputs are active. So if I add a voltage on a binary input, then I will get here this check mark. Oops, now I touch the mouse wheel here. On the other hand, I can also activate binary outputs during commissioning. I can click them through, and all the time when I click here on a binary output, then the contact will close, for example. And then I can measure, for example, is the wiring in the cubicle correct, by just going on the terminals of the cubicle and not need to search where is now this terminal connected to on the relay. I can inject also currents and voltages, and I have here a vector diagram, a phasor diagram of the current and voltages. I can use this tool multiple times and connect each time one tool with another relay. So I have then different screens, and then I can also test the interconnection, the wiring between relays, by activating the binary output of the first device and then see if the proper binary input of the next device is activated or not. And I switch between various screens. So also the wiring between relays can be checked in a relatively comfortable way here. Good. Last tool, the cProtect Digital Twin, which I personally use most, I think, of all these tools, because I have a digital image of our cProtect 5 relays, And it's not just a fun firmware that is running there, it's the original firmware but which you get. That means the behavior, what you see here of these relays, is very, very close to the original behavior, so the behavior of the real relay here. Here's an example where you can inject voltages and currents, and you play this on the relay, and then the relay makes a tripping command. I use this very often when I create CFC charts to check the CFC charts. We have an online simulation, so for this you need a relay, and then I use a digital twin, and then I connect the Dixie with the digital twin here, and then I can verify my CFC chart, a very comfortable thing. Another possibility, I don't now list all the things here. We have separate tutorials and webinars about all these tools. So if you're interested, have a look in these webinars there. Just one more thing which I would like to mention. You can also replay fault record. So if I have a fault record in a COMTRADE format like this here one, then I click here, I select this before and make some configuration. Then I click here on this button, start button, and then I replay this fault record. Here I can visualize the fault records, the traces here, and then I can replay this onto the relay, and then the relay and see what is the relay behavior. So also one of my tasks, if I get fault records, then I replay them and see what is the behavior of the relay. If I need additional information, I can link them in, I can change settings and so on. So this would be also another point of this cProtect 5 digital twin. There is more to that, but due to the time we have already used up, let's say, I would like to stay with that short introduction of these additional tools, hoping that this was a little bit helpful, and maybe if you don't know these tools, that you can go further and have a look in other webinars or get information from our webpage or from our colleagues. So then I come to the last point, and this is the application guide for the cProtect 5 motor protection. With this link, which you have then in the PDFs, you can directly go to the CEOS portal and download it from there. A quick look inside. I have it here. This is now the front page, the first page here, the index. Basically, we have 83 pages of motor protection examples and explanations, the basics of synchronous, asynchronous motors, overview of the protection function, the thermal discussion, thermal stressing of motors, then a special chapter for sensitive ground fault protection, which I did not treat now in these two tutorial sessions, current transformer requirements, and then 2 or 3 examples, setting examples I showed here on these slides. One is for an asynchronous motors, medium-sized asynchronous motors, and then on the next page, high-power asynchronous motors. There is also, I think, the principle with a Korndorfer starter explained inside, so an auto transformer, which is used to start a motor, and also a protection example for synchronous motors. Good, so if you're interested in more technical details, I can recommend you to have a look into this brochure here or application guide, or you follow that link here in the slides, or I think we put it also separately in the documentation of this webinar. Good, with this, I would like to conclude my, sorry, a little bit longer presentation. Are there still some questions left? And
Yes,
let's try to answer them.
At least I've seen 2, and I've seen that at least 50 people still stay with us. So it was interesting what you told. Thanks for staying. And then let's see, the first question from GH. How much time for
inhibition?
Probably inhibition, the 60 or inhibit. 66, the example motor has about 5 megawatt ampere. Oh, that's probably a thank you. Okay.
Difficult, because this depends on the motor data. I cannot give you a recommendation how to set this function if I don't have the motor data. I tried to show you with one example how to make this setting. basically you need somehow a statement, so and so many starts from cold and warm state of the motor, and then the starting time and starting current for which these statements belong. Yeah? So for example, a normal startup with a normal current, a normal voltage, and then the times, and then, well, you get the times out of the curve, for example, and then you have the number of starts, and with this data, then we can create this, or this function is then running in the relay at the end.
All right. And last question, a bit of clarification or an addition to the question we had before the breaks. Is there any available application for the this offline earth fault monitoring? And then it's the addition there. The application is for motors in explosive or hazardous areas that cannot be energized to a ground fault.
Okay, so maybe I think we discussed this best in a direct discussion one-on-one. Maybe it's helpful for me to have maybe a single line diagram. This is always good. And I can just invite you to discuss this one-to-one. And then if we come to a certain result, I can put this also here in the answer box, maybe with an example. Then everybody can profit then from the result fully.
So either RA, please contact Klaus directly, or the other way around. We'll, I think we have the mail address, and you will have the chance to go on a one-on-one discussion.
Okay.
Thank you. I do not see any more questions right now. Thanks, Klaus, for the comprehensive insight once again into motor protection. Thank you for staying that long with us in the line. It seems like it was valuable content and that it's valuable for you. So I hope you will stay with the electrification and automation webinars. There is more to come around protection, not only motors, but more. Just visit us on our EA webinar website. Stay safe for now. Keep your systems protected and see you in one of the next webinars. Goodbye for today.
Goodbye.